Alrighty guys, so today we are going to discuss our final topic or last module for exam 3, and that topic is problem solving. Alright, so one of the best ways to start off this topic is to simply ask you guys what sort of problems you have solved lately, right? So when I typically ask my cognitive psychology students this question, I typically get answers like, well, I've solved problems in my physics and math and chemistry courses, right? Or if you think more abstractly, I have solved the problem of figuring out how to turn in all of my assignments on time. Or maybe I have managed a relational conflict, maybe with a friend or roommate or a significant other, right? So these are a there's kind of a wide disparity between the nature of all of these problems, but they all seem to fit a singular definition, right? So how do cognitive psychologists define problems? Well, the definition that they've come up with is a problem occurs whenever there is an obstacle between your current state and where you want to end up, or your goal state, right? So there's an obstacle between where you are now and where you want to be, and it's not immediately obvious the steps you should take to get around that obstacle, right? So in problem solving, we're trying to progress from our current state or present state to a goal state. And in order to do that, we have to figure out how to get around an obstacle. So research by psychological scientists investigating problem solving has focused on basically two different objectives, right? So the first objective is simply to study the mental processes that occur as a person is attempting to solve a problem, right? So what are the underlying cognitions that are part of problem solving? And the second one is very similar to research in the field of learning and memory, right, where psychologists work with textbook companies and teachers and professors to optimize their instruction. Psychologists specializing in problem solving often attempt to come up with kind of interventions or strategies people can use to make problem solving easier and more effective. Okay, so that's what we're going to focus on today is what are the underlying cognitions associated with problem solving, and how do we optimize problem solving? Okay, so the structure of this lecture is going to be very similar to the structure of our lecture on judgment and decision making, right? So just like before when I gave you guys different activities that I wanted you to solve in a worksheet, I've done the same thing for this module. So there's 3 different activities for you guys to do. And each of those activities corresponds to a particular, in this case, a particular problem that psychologists have studied in the laboratory, right? So if you haven't done so already, please go ahead and pause the video and go back and download the activity sheet from Canvas and go ahead and complete those 3 activities. Again, I'm not going to collect them for a grade, but I think it'll be a lot easier for you to understand things going forward if you've tried to solve those activities yourself. Okay? All right. So the first activity I asked you guys to do, or the first problem I asked you guys to attempt to solve, is something called the candle problem. the candle problem. So this particular problem asks you to imagine that you are led to a room that contains a table. And on that table there are three objects: a candle, a box of matches, and a box of thumbtacks. Your task is to find a way to attach the candle to the wall of the room so that it burns properly using no other objects than those on the table. Right? So what solutions did you guys come up with when you tried this activity yourself? Well, some of the most common solutions I get from students is maybe they try to melt the candle, right? And then the melted wax has some kind of adhesive or gluey texture, right? That sticks the candle to the wall, right? So that's the most common solution that I get from students, but that's actually not the answer. So let's go ahead and explore what the answer to this problem is. Okay. So the solution to this problem occurs when a person realizes that the matchbox can actually be used as a support rather than a container. Right? So what you can do is you can dump out the matches of them and use the matchbox, right? And use the tacks to affix the matchbox to the wall, right? And that effectively is used as a shelf to hold up the candle, right? So why are psychologists interested in studying this particular problem? Well, to answer that question, I'm first going to tell you about two different experiments that were conducted using this problem as the basic task that participants solved. Okay? So in one experiment, this problem was presented to a group of participants. And when they received the materials, they were given small cardboard boxes containing each of the items. So they received a small cardboard box full of candles, a small box full of tacks, and a small box full of matches, right? So in that case, these boxes were clearly being used as containers for items. But then another group of participants were asked to solve this same problem, but in that case, they were given the same materials, right? So they were given the matches and the candles and the tacks, but they were outside of the boxes, right? So they received candles, matches, and tacks, and then 3 empty boxes. And what the researcher found is that when he compared the performance on this particular problem between those two groups, he found that the group that had been presented with the boxes being used as containers found the problem much more difficult to solve than the group that was presented with the empty boxes, right? And then this was replicated actually in 1952 by Robert Adamson. So he repeated the original experiment and got the same exact results. So when participants were presented with the empty boxes before solving the problem, they were twice as likely to solve the problem effectively than participants that had been presented with the items in containers. So again, before we talk about why this is interesting, I'm going to present you guys with one more problem. So this is called the two-string problem, right? So basically, your objective in this problem, right, is you're given a chair and a pair of pliers, and using just those items, you need to tie these two strings together, right? But inevitably, what you notice if you try to solve this problem is that the strings are too far apart, right? So what happens is you end up reaching for one of the strings, and then your arm isn't long enough to reach the other one, right? So how do you solve this problem? Well, to solve this problem, participants need to tie the pliers to one of the strings and create a pendulum, which can then be used to swing the other string within the person's reach, right? So two things are particularly significant about the two-string problem. First, 60% of participants who are given this problem did not solve it effectively. And the reason is because they're too focused on the typical function of pliers, which is to, grab things and twist them rather than functioning as a weight. Right? The second thing to notice is that when Meyer, 1931, took another group of participants and asked them to solve the problem, right? Instead of just leaving them to their own devices, this researcher tapped one of the strings so that it started swinging back and forth. And when the researcher did that, 23 out of 37 participants who hadn't solved the problem after 10 minutes, right, suddenly were able to solve it in 60 seconds, right? So seeing the string swinging from side to side apparently triggered the insight that pliers can be used as a weight to serve as a pendulum that creates that swinging motion. So what does this mean? What do the candle problem and the two strings problem have in common, and why are they interesting to psychologists? Well, the reason is because they both illustrate something called functional fixedness. Okay, so functional fixedness is the tendency to think about objects in terms of their typical or customary uses, right? So both the two strings problem and the candle problem require you to use these objects in an unconventional way, right? So in the candle problem, instead of using the box of matches as a container for matches, you're instead using it as a shelf or a support for the candle, right? And in the two strings problem, you're using the pliers as a weight or pendulum rather than to twist or pick up objects, right? So what makes these problems so difficult to solve by themselves, right, is that particularly in the first case of the candle problem, where you're given the 3 boxes of the materials, right, is you're led to think about the objects as you would normally interact with them, right? And that prominent response or that prior experience is almost going to have a blocking, right, or interfering effect, right? Because those typical uses are going to become very prominent in your mind, right? You have a lot of experience using those objects in the typical ways. So trying to think outside the box, so to speak, and come up with a more creative and atypical use of them, right, is going to be much more difficult than it would be if you didn't have any prior experience with that object. So one thing I wanted to illustrate here is that even though we all experience functional fixedness, and we all have a lot of difficulty with the candle problem and the two strings problem unless we know the answer beforehand, right? So we all experience that blocking or fixation from prior experience. It is possible to overcome it. So it is possible to think about objects in a creative way. So this is actually kind of an internet sensation. So I went ahead and posted a viral video for you guys in the slides. So if you haven't already, please check it out. So in this particular video, it's just kind of a mashup or a compilation of videos of people coming up with kind of silly, crazy things you can do with everyday objects, right? So it's an illustration of overcoming functional fixedness, and it's kind of funny. So go ahead and check that out. And the other example I wanted to give you of overcoming functional fixedness is a personal example of mine. So as I think some of you know, I have a disability. So the disability that I have is cerebral palsy. And basically there are many different subtypes of this particular disability. But the kind that I have basically creates or is caused by what's called muscular spasticity, right? So what spasticity refers to is just having muscles that are very, very tight, or having muscles that are contracted all the time, right? So it's very, very difficult for individuals like myself with this condition to relax their muscles, right? And so what happens as a result of this disorder is you can develop what are called contractures, which are basically the permanent shortening of muscles, right? So your muscles literally start to shrink because they've been so contracted or so tight all the time. And so one of the ways that they treat muscular spasticity, particularly in children, is that they do surgeries called muscle lengthening surgeries. So with muscle lengthening surgeries, they literally open you up and take those shortened or contracted muscles and stretch them surgically, right? And if you're a child with cerebral palsy, you might have this done 2 or 3 times in your childhood, right? So that was the case with me. I had it done about 3 or 4 times. And each time that I had it done, I had to wear these leg casts for about 6 to 8 weeks. So you might imagine that that's kind of a challenge for a young kid that likes to run around and do stuff. And one of my favorite activities at that time in my life was I really liked to listen to country music. So I liked, Garth Brooks and Faith Hill and all those folks that you guys probably don't even remember. Or you weren't even born yet when they were really famous. But and so obviously this was in the 90s. So I didn't have like an MP3 player or anything like that. So I had to actually listen to what they call a boombox, which is this big monstrosity that has a cassette player and a CD player and a radio in it. And one of the things that I would have to do is my boombox would only work if the lights in my room were turned on. So one morning I was sitting on my bed and I wanted to listen to my CDs, and I had to turn my light switch on, right? But the light switch was all the way across the room, and I couldn't stand up to turn my light switch on. So what I ended up doing is crawling kind of on my stomach across the room. So I got to where the light switch was, but I still wasn't tall enough to actually turn the light switch on. So I started sort of looking around my room, looking for something that I could use to kind of, prop that light switch up. So I started to look for like a stick or something long to use, but I noticed I didn't have anything like that. But what I did have is I had a box of Crayola markers sitting on my little art table. So I went over to my box of Crayola markers, and one thing you guys might remember about Crayola markers is they all fit kind of into each other, right? You can stack them on top of each other, right? So that's what I did. I stacked all of my markers on top of each other and basically created a giant stick out of the markers, and I used it to turn the light switch on, right? So that's kind of a long-winded example, but it illustrates that this is something we have the capacity to do, right? It might not be our first response, and like I said, there's going to be some blocking or interference because of our prior experience with those typical uses. But that experience can be overcome, and we can actually generate creative solutions if we're ever put in a situation where it's adaptive to do so, right? So obviously in the laboratory, people aren't going to be particularly motivated when solving kind of an abstract problem. But the truth is that in the real world, right, in vivo, all of us are occasionally faced with situations where we have to use objects in an atypical or not customary way, and we all have the ability to do that. Okay, so the next problem I asked you guys to solve is something called the water jar problem, right? So basically the objective with this problem is to end up with the desired quantities specified in the rightmost column there, using only the 3 jars that you're given, right? So as far as solutions to this problem, many of you might have noticed that all of the problems can be solved by the following formula. So you start with B, you subtract A, and then you subtract 2 of C, right? So B minus A minus 2C. That formula will solve all of the problems that you were given, all 8 of the problems. Fewer of you might have noticed that there's a much simpler solution for problems 7 and 8. So for problem 7, you can simply add A and C together, and for problem 8, you can subtract them. So number 7 is A plus C, and number 8 is A minus C, right? But like I said, it's very likely that most of you never noticed that there was a much simpler solution for 7 and 8, and instead chose to solve all of the problems using the same formula, right? So this is another illustration of how prior experience doing something can actually impede successful problem solving, or at least make it less efficient. So the water jar problem illustrates something called mental set. Right? So mental set is simply the tendency to think of a problem in a typical or customary way, even when a better solution is available. Right? So let's look real quick at some experiments, right, that gave this problem to participants to see how well they could solve it and what solutions they applied to it. Okay, so the first psychological experiment using this particular problem, the water jar problem, was conducted by Lutjens in 1942. And he basically compared two different groups of participants. So his first group of participants he called the mental set condition. And in that condition, he first did problem 1 of the 8 that you guys just solved. He did problem 1 for the participants as a demonstration, right? So this was considered the mental set group because it already established the B minus A minus 2C rule, right? So it already gave participants prior experience using that rule, right? And in the no mental set group or the control group, participants just solved problems 7 and 8 without any of the earlier problems or without a demonstration, right? So they started with problems 7 and 8 and had no prior experience with the B minus A minus 2C solution, right? And what he found, the result, was that only 23% of the participants in the mental set group used the simpler solution for problems 7 and 8, but all of the participants in the no mental set group used the simpler solution, right? So again, what this illustrates is that prior experience or having used a solution to a particular problem in the past, right, can make us less able to find and utilize simpler solutions in the future. Right? So again, just like with functional fixedness, mental set shows us that prior experience can sometimes impede effective or efficient problem solving. Okay, so the last problem I asked you guys to solve was the radiation problem. Okay, so the problem says, suppose you are a doctor faced with a patient who has a malignant tumor in his stomach. It is impossible to operate on the patient, but unless the tumor is destroyed, the patient will die. There is a kind of ray that can be used to destroy the tumor. If the rays reach the tumor all at once at a sufficiently high intensity, the tumor will be destroyed. Unfortunately, at this intensity, the healthy tissue that the rays pass through on the way to the tumor will also be destroyed. At lower intensities, the rays are harmless to healthy tissue, but they will not affect the tumor either. What type of procedure might be used to destroy the tumor with the rays and at the same time avoid destroying healthy tissue? Okay. So students often have a lot of difficulty solving this problem, right? So what is the solution to this particular problem? So the solution to this problem, which less than 10% of people came up with in the Gick and Holyoke 1980 study in which this problem was presented, is simply to bombard the tumor in the center with a number of low intensity rays from different directions, right? So basically converge upon the tumor with a bunch of low intensity rays And what that does is it destroys the tumor from the center outward. And because all of the rays are low intensity, you don't have the problem of damaging surrounding tissue. So interestingly enough, a medical technique that's utilized in the treatment of brain tumors called radiosurgery uses the same procedure, right? So you eradicate brain tumors by converging a number of different gamma rays on them, or gamma knives, I think they're called. And that destroys the tissue without damaging other regions of the brain in the process. But as I said, it's very, very difficult. So Gick and Holyoake found that, like I said, less than 10% of people were able to solve the problem when they were given the problem by itself. Right? So one of the things that they did in subsequent experiments is they gave them another problem before the radiation problem, right? So the problem that the second group of participants was given first is something called the fortress problem. So the fortress problem says, suppose you are a general trying to capture a mighty fortress. The fortress is at the center of a country that has 5 roads leading into it from different regions. Each of these roads has been mined to defend against large attacks, but to allow for small parties of farmers to travel safely. The mines will explode only if 3,000 or more people are on the road at once. In order to capture the fortress, you need to bring your entire army of 10,000 people to its walls at almost the same time. If the soldiers arrive too gradually, the smaller groups will be defeated by the fortress's defenders. How can you bring the whole army to attack the city at once? Well, the solution, right, is identical to the solution for the radiation problem. So the solution is to send small groups of soldiers down each of the roads, coordinating their movements so that they all arrive at the fortress at the same time. Right? So just like we're using small intensity rays to converge upon the center of the tumor, we're sending small groups of soldiers to converge upon the fortress. Right? And when participants were given this problem beforehand, right, that number of 10% increased to 30%. So in order to get a significant proportion of participants to solve the radiation problem successfully, they not only had to see a problem with the same solution, right, but they had to be told that that solution is relevant to the radiation problem. Right? So just giving people the problem isn't significant. You have to reveal to them that the solutions are analogous, or that the structural features of the problem are analogous. Right? So now let's turn our attention to what cognitive processes are happening when people attempt to solve the radiation problem using the fortress problem as an example. Okay, so this process of solving one problem using the same technique that you learned on an earlier problem is called analogical transfer, right? So with analogical transfer, once you identify the solution to one problem, you can utilize the same technique on future problems provided the underlying structure is the same. So what analogical transfer requires you to do is reason from the previously solved problem called the source problem, in this case the fortress problem, to a new unsolved problem called the target problem. Right? So the source problem is the fortress problem, and the new target problem is the radiation problem. Right? So what are the specific processes that you have to go through in order to transfer the solution to the fortress problem to the radiation problem? Well, first, you have to notice that there's an analogous relationship, or you have to notice that those problems are similar to each other, right? So noticing that there is an analogous relationship between the source problem and the target problem. This step is obviously going to be really crucial in order for analogical problem solving to work. However, as we've seen, or as I've talked about, most participants need some kind of prompting before they notice the connection between the source problem and the target problem, right? So Gick and Holyoake consider this noticing step to be the most difficult of the three steps, right? And a number of experiments have shown that the most effective source problems are those that are most similar to the target problem, right? So when I say similar, I don't mean just similar in terms of the underlying or structural features, but also the surface features, right? So one of the things that's difficult about reasoning from the fortress problem to the radiation problem, right, is that the topics are totally different, right? So the solution is very, very similar, but the objects that you're thinking about are very, very different. So subsequent research has shown that the best analogical transfer happens when the objects or the kind of the physical features of the source and target problems are similar to each other. Okay, so next you have to map the elements between the source and target problems, or you have to map the correspondence or similarity between the source problem and the target problem, right? So to use the story to solve the problem, the participant has to map corresponding parts of the story into the test problem by connecting the elements of the source problem, okay, to the elements of the target problem. So let's look at that a little bit closer. So if we were successfully mapping the elements across these two problems, we would see that in the first problem, the fortress corresponds to the tumor, right? This is the object that you're converging upon. The mined roads are going to correspond to the surrounding tissue, right? So these are both very fragile things, right? So the mined roads can only hold so many soldiers before they blow up, and surrounding tissue can get destroyed even at very, very low intensities. And the attacking troops, right, is that converging process. So bringing many, many troops together down the mined roads, or bringing many, many low intensity rays together, right? So the small groups of soldiers are going to converge upon the fortress, and the weak rays, or the low intensity rays, are going to converge upon the center of the tumor. Okay. And lastly, once you have successfully mapped each of the elements from the source problem to the target problem, you obviously need to generate a solution and apply it to the target. Okay, So applying the mapping to generate a parallel solution to the target problem. So this would involve, for example, generalizing from the many small groups of soldiers approaching the fortress from different directions to the idea of using the weaker rays that would approach the tumor from different directions. So noticing and mapping, like I said, are arguably the most difficult steps in analogical problem solving. Okay. So let's go ahead and look now at the data obtained by Gick and Holyoake, just to review. Okay, so again, like I said, when no hint was provided, when they were given the radiation problem by itself, less than 10% of participants solved it. This number jumped up to 30% when they were given an analogous problem, but they weren't prompted that the fortress problem could be used to help solve the radiation problem. And we got a little over 70% of participants to generate the correct solution when the fortress problem was provided with the explicit instruction that they could apply the same solution to the radiation problem. Okay, so in general, like I said, participants do not produce corresponding solutions with any great frequency unless given a hint, right? So these results demonstrate the difficulty of recognizing the relevance of one problem and its solution to another, right? So analogical transfer is very, very difficult, at least that's what laboratory studies would suggest, is that we're not very good at using analogies to solve problems and noticing correspondence or similarity between problems. Okay, so what are some ways to optimize problem solving? So remember I told you guys that cognitive psychologists are interested in developing interventions that make problem solving more efficient or more effective, right? So I'm going to show you two experiments that illustrate how we can help people with analogical transfer. So in this first study, participants were given two sets of instructions, right? So participants in one group were told to analyze a series of algebra problems one by one, okay? And another group was instructed to compare each of the problems to each other, right? So one group solved the problems, and the other group simply compared the problems to each other, attempted to notice what the problems had in common, right? So this is an example of that mapping procedure. And what they found is that when participants were given new problems later on, those who had been forced to consider what the problems had in common, because they were thinking about the underlying structure of the problems, right? So they were ignoring the surface features and rather focusing on how the problems might be solved, okay? They were better at using those same problems to solve new problems later on than participants that had just worked to find solutions to the problem, right? So anytime we can think about a problem in terms of its underlying structure, kind of ignoring those surface features, the more successful we're going to be. Okay, another example, participants were again given problems, and one group was told to memorize the problems. So memorize the features of the problem and the solutions to the problem. Another group was told to work on understanding the solution and understanding it well enough that they could teach it to somebody else. Okay, so the people that were told that they were going to have to prepare to teach someone else the problems, were able to solve 90% of brand new problems successfully, right? So again, they're transferring what they learned about the underlying structure of the problem. And this compared to memorizers, right, who were only able to solve less than 70% of the new problems successfully, right? So again, this illustrates the importance of not getting stuck on surface features, but rather thinking about the deeper structure of the problem. Okay. So one final thing I wanted to note is that psychologists haven't just focused on solving problems in the laboratory. They've also looked at more naturalistic or real-world settings in this domain, right? So they've looked at, for example, scientists and inventors and watched them as they're engaged in conducting experiments or developing products to see how they solve problems kind of in the real world, right? So the advantage of this is that it's much more akin to what actually happens or how we actually use our cognition. So it has really good external validity, right? But the disadvantage is that it's very time consuming and it often costs money, right? People don't let you just kind of show up at their lab meetings or their place of business unless you offer some kind of monetary incentive. And it's also got the main drawback of naturalistic studies from a scientific perspective, in that we can't really isolate or control variables or manipulate anything. So it's lacking what we call internal validity. But one of the things that becomes very, very obvious is that while people sort of characteristically are struggling to solve problems in the laboratory, right? So we see this absolutely in the Gick and Holyoake experiments, but even before we were talking about analogies with functional fixedness and mental set and so forth, right? So all of these experiments lead us to the conclusion that we must be really, really bad at problem solving. But in fact, all of the naturalistic or real world research seems to suggest that we're actually really, really good at problem solving. And particularly, the use of analogies seems to be quite common. And even as a characteristic feature of the process of discovery, right? So the process that scientists and inventors go through, right? So in one case, they looked at molecular biologists and immunologists, and they videotaped them during their lab meetings. And they found that when they counted the number of analogies that the researchers used per hour, that they used 3 to 15 analogies in just the span of 60 minutes, right? So for example, if E. coli works like this, maybe your gene is doing the same thing, right? So just like we use maybe the solar system as an analogy for subatomic particles, right? And so on, analogies seem to be particularly effective in the process of scientific discovery. Similarly, they also looked at engineers and how they develop new products, particularly those with medical applications. And they found that in the span of an hour-long meeting, engineers often propose an analogy every 5 minutes, right? So again, what this illustrates is something called the analogical paradox. And that is that universally, in a number of different laboratory studies, we seem to have a lot of difficulty solving problems that require analogical transfer. So we have a lot of difficulty generalizing from a source problem to a new target problem. But in reality, particularly during the process of discovery, right? People do tend to use analogies quite often to aid other people's understanding or to propose new theories, right? So all that is to say, even though the laboratory evidence suggests that we're very poor at problem solving at times, we are very effective in the real world, just like scientists and inventors and engineers. And me as a little girl with my markers, right? We all have really an astonishing capacity to all sorts of advanced cognition in this domain when given the opportunity to do so. All right, guys, so that concludes our discussion of problem solving and our last lecture for the semester. So thank you so much for hanging in there with me. I hope these videos were helpful and I hope they made sense. And certainly if you guys have any questions, as always, feel free to reach out to me. Okay? Have a great day.